we deal with a new chapter, second order ODE. In the first chapter, we discussed first order ODEs. So the first section is about the linear second order ODE. So you can compare with the first order linear ODE. You can see that this second order ODE has the second derivative of a function y of x plus a function of x times the first derivative of y and plus a function of x times y equal to a function of x. And this ODE actually is the standard form of a second order linear ODE. Okay. As in first order linear ODEs, we will first consider the homogeneous case when r of x is equal to 0. And again, P of x and the Q of x are co-coefficients. Okay, so these two functions of x are co-coefficients of linear ODE. A simple example is that y of prime plus y equals 0, where p of x equal to 0 and the q of x is 1. Okay, so consider very simple one. You can check one is cosine x and so it's quite easy to check why. Since we know the second derivative of cosine x is okay, because that the first derivative of cosine x is minus sine x, right? And we take the derivative again, so this is minus, and the derivative of sine is cosine. Okay? So the second derivative of cosine function is equal to the minus cosine function. Again, the second derivative of sine x, okay, is yeah, because the first derivative of sine x is cosine x. Okay. And once again, this is okay. And when you move minus cosine x to the left-hand side, we find that cosine x satisfies this differential equation. Similarly, if we move minus sine x to the left-hand side, we will see that sine x satisfies this differential equation. Any questions? Yeah, just because checking is usually very simple, right? Because you know a lot of things about derivatives of dimensional functions. Yeah. There is a theorem, 1.1, we call the superposition principle. Right? The superposition principle it is a fundamental principle to discuss linear ODEs. All right? Let me state a statement. So it says that for a homogeneous second order linear ODE, like this one, okay. If y1 and y2 are two solutions for this ODE, then we can make a linear combination. Namely, we times y1x by a constancy, times y2x by another constancy, and add them together to form a new function. We call it y of x. This new function must be a solution of this homogeneous linear ODE for any C1 and C2 in the set of all real numbers. So it is called the superposition principle. Okay, so this is actually the superposition of two functions. Any questions about the statement of the theorem? Okay. Now the proof is quite simple. Alright. Since y1x and y2x are solutions of this ODE, so we can find y1 prime plus p of x, y1 prime plus p of x, y1 equals 0. And the y2 function, y2 double prime plus p of x, y2 prime plus q of x, y equal to 0. Okay. Now, we multiply okay, so we multiply a constant C1 on both sides, the left hand side and the right hand side. Also, we multiply a constant C2 on the left hand side here and right hand side. And then we add them together, right? So we have C1 plus zero. Okay? So this result is a purely algebraic result. Now, we know derivative is linear. Okay? So we know that actually this is equal to C1 y1 plus C2 y2 right. And this is C1 y1 plus C2 y2 right. Zero. Okay. So equal. Okay. And we know this is equal to y. This is equal to y. So finally, we have y plus p of x, y plus q of x. Okay, and the time. Because y satisfies this. So the reason that we have identity is because derivative taking the derivative is linear. Okay? So you know this fact from calculus. Right? Namely, if we want to find the derivative of the sum, okay, actually this is equal to, you are finding the same linear combination with the derivative respectively. Any questions about the proof? Okay. So we can see, once we find two solutions, we can find infinitely many solutions. Even though we know zero, the trivial solution, zero function must be a solution, right? The trivial solution. Function, right? So once we have a solution, we can multiply with any constant, right? And we have infinitely many solutions. Example, Right? Consider consider non-homogeneous second order linear ODE. Okay, so it's a little bit different from this one. This one is homogeneous, but this one is not homogeneous because we have a non-zero Rx on the right hand side. So this is zero. Okay. You can check. Y1 and okay, are two solutions of this ODE. Okay. So it is very simple to check that y1 sin x plus 1 satisfies this ODE, and sin x minus 1 also satisfies this ODE. Okay. Check them. But which is equal to C1 okay, C1 is not a solution of ODE with C1 plus C2 not equal to 1. Why? Well, you can, so y double x, okay, is equal to minus C1 sin x sin x. Okay, and this one is minus 1 okay, because y is equal to, this is superposition plus C1 plus C2. So this sum, the function in the parentheses, is equal to y minus this constant. Okay. So we have okay, and this is equal to 1. Okay, so the superposition principle is violated. Why? Because we are talking about non-homogeneous ODE. The superposition principle only holds for homogeneous linear ODE. Okay? So, if it is not homogeneous, in general, not superposition So from this example, we can see, in general, non-homogeneous second-order linear ODE do not have superpositions. Another example, a nonlinear ODE. Okay, so 1 4 times 1 and x equal to 0. Okay, so consider it is nonlinear because we have a term which is the product of the second derivative y and y. So it is nonlinear. Okay, so you can check that y1x equal to x squared and fx equal to 1 are two solutions. Okay, just check it because this is polynomial, right? So you can check that. But neither minus y1x nor y1x plus y2x, which is equal to x squared plus 1, are solutions of linear ODE. Okay, so even though you multiply the y1 by minus 1, you can see minus x squared is not a solution of this ODE. Okay. Or you can add these two solutions together, which is equal to x squared plus 1. This function is not a solution of this nonlinear ODE. Okay. So that's nonlinear ODE and not the superposition principle 2. The position principle. Okay. Now, from our example, homogeneous linear second order ODE, we quite often to find two solutions which are linearly independent, which are in the following sense. Alright? So we say two solutions. So this is the definition of two linearly independent solutions. Okay. I know some of you have taken linear algebra last semester, but some of you currently take linear algebra course in this semester. So indeed, linear dependence, the concept of linear dependence here is the same as the linear independence in the course of linear algebra. Okay. But you have to regard functions as a vector. Okay. So, just think about this is a new definition. Okay. So we say two solutions, y1 and y2, for homogeneous second order linear, or it's called linear dependent. If we form a superposition alpha and beta together such that it is equal to 0, okay? So if we can form 0, and it is 0 for all x in an open interval, means that this is identical to 0. So it's a zero function. So actually, it's a zero function. And so if this is true, then we must have alpha equals 0 and beta equals 0. This is the only possible choice. Okay. So it says that if either alpha is not equal to 0, or beta not equal to 0, then this superposition is not zero functions in an open interval. Okay? even only if alpha y1x and beta y2x is not a zero function of fx in any open interval. Or any alpha, beta, not both zero. Okay? So this is another way to speak about two linearly independent solutions. So we say two solutions are linearly independent if we form a linear combination by two constant alpha and beta, and not both zero. So at least one is non-zero. Then this linear combination is not a zero function. Okay, it's not a zero function in any open interval. This is more clear than the statement in definition. Example, y1x equals to consider right now y1x, you know, cosine x is the solution, and y2x 3 right. So we have two solutions. But these two solutions are linearly dependent. Why? Because that 3 y1x minus y2x equals to 0 for all x in R. Okay. So in the whole VR. So think y1x and y2x are linearly dependent. Because we find coefficients, right? We find coefficients which are not both zero, right? One is 3 and this is minus 1. And the linear combination becomes to all zero functions. Right. So it is linearly dependent. Because if these two functions are linearly independent, then if we find a linear combination which is zero in an open interval, then by the definition, these two coefficients must be zero. But this is not true for this case. So y1 and y2 are linearly dependent. Now y3x, okay, another solution or D, right? Another solution. Okay. No solutions. All right. So we form linear combination. So if alpha plus beta so equal x is 0 for all x in R, then right So if we form a linear combination and we say, we ask that this is equal to 0 for all x in R, then alpha cosine x plus beta must be equal to 0, right? For alpha. Then, by evaluation, then by making x equal to 0 and pi over 2, okay? X equal to 0 and x equal to pi over 2. Actually, this is equal to 0 for all x in R, right? So we just take two x values. We have alpha times 1 plus beta equal to 0. And we have alpha times 0 plus beta times 1 equal to 0. Right? And this implies that alpha equals to 0. This implies beta equals to 0. Right? So immediately, we have alpha must be equal to 0. And the beta must be equal to 0. So by this definition, if we want the linear combination to be 0 for all x in an open interval, if this is true, then we conclude that alpha and beta must be 0. Right? So we prove that's y1x and the y3x are linearly independent solutions of this argument. Is that clear? Okay. So to show two functions are linearly dependent, we just find two coefficients, non-zero, not both zero, such that the linear combination equals 0 for all x in the open interval. Alright. But to show two functions to be linearly independent, okay, then we have to verify. Once we ask this is true, then alpha and beta must be 0. We have to prove that. Okay? Once done, then you are sure that these two solutions are linearly independent. Alright, so these are standard procedures to do the proof. Any questions? All right, now a general solution, okay, of a homo Okay, so we give general solutions of a homogeneous second-order linear ODE, right? With any solution which is in this form. So actually, this form is a superposition, right, of two linearly independent solutions, y1 and y2. Okay. So from this definition, you know, to find a general solution for a homogeneous second-order linear ODE, you have to find two linearly independent solutions. Okay, you have to find two linearly independent solutions. And later on, we will show this homogeneous second-order linear ODE must have a general solution. So general solution always exists for homogeneous second-order linear ODE. So we will show that later. Right? But at this moment, I just give you what is a general solution look like. Okay, so this is one, and how do you find out a general solution? And it is equivalent to find out two linearly independent solutions. Okay, so before working out specific examples, all right, and we can give one more definition. Okay, so two initial conditions right? Y is x0 equal to k0 and the y from x0 equal to 1. Okay. Two initial conditions are used to determine the two arbitrary constants C1 and C2 in a general solution. Okay, so the general solution has two arbitrary constants, C1 and C2. So we use two initial conditions, y x0 equal to k1 and y prime x0 equal to k1, right, to determine C1 and C2. Next, and second order ODE together with two initial conditions. And initial value problem. Initial value problem. Okay. So now, recall, for first order ODE, we need only one initial condition. So one first order ODE together with one initial condition becomes to an initial value problem. But for a second order ODE, we need two initial conditions. Okay? So for a second order ODE, together with two initial conditions, like this one, is called an initial value problem. Okay? And from the homogeneous linear ODE case, you know why we need two initial conditions. This is because that the general solution consists of two arbitrary constants. Right? So now we need a useful technique to solve second order ODE in many situations. It's called the method of reduction. Of order. Okay? So it's called the method of reduction of order. The meaning is that we will transform a second order ODE to a first order ODE. So we have order reduction. Okay? And we learn a lot of techniques in chapter 1 to solve first order ODE. Okay? So this is the main idea. Alright, so let's take an example first. Now, this method of reduction of order, alright, need to know one solution. So inspection, so we inspect that. Inspection shows that y1x equal to x is a solution of this ODE. Okay, so we can just do the substitution. We will find out y1x, the polynomial x, the degree 1, the polynomial degree 1, is a solution of this ODE. So now, to find a general solution of this ODE, we need to find, oh, thank you. So we have to have a rest for about 10 minutes.